So we have a bunch of stuff that's new on the course webpage. Let's go through that a little bit. The principal thing is a new block of text on our lecture notes for today, which is not 32 pages long. That's a mistake on my part. It's 83 pages long that we'll be looking at for most of today. Then there's a handout for those of you who want to use R to create handouts like the ones I've been giving here. There's some stuff that shows you how to use R to create multiple plots on the same function, plots of multiple functions on the same graph. And so here's a little example with, it's hard to see one of them, but it's meant to be 3 different Gaussian curves, and you can use the plot and line commands followed by the text commands to label things. So that may be helpful to you if you'd like to see how things are going in R. Then there's a copy of this guy, which we're looking at now. We're going to be talking today about the metropolis algorithm. There's a powerful human desire to rank things at every possible moment. And so toward the end of the 20th century, perhaps in the year 2001 or so, some people who believed that they were in a position to stand in judgment made a ranking of the top 10 algorithms of the 20th century. I guess it was people writing in something called Computing in Science and Engineering, comes out of the IEEE, and not in any particular order other than chronological, so not claiming that this is the most important algorithm, but chronologically the very first of the top 10 algorithms is the one we're going to talk about today, the metropolis algorithm. And then you'll see lots of other old friends here, George Danzig with the simplex method, and Householder's matrix decompositions, the Fortran optimizing compiler. They regard the building of the compiler as an algorithm, which is a pretty interesting thing to say. And then the QR algorithm and quicksort and the fast Fourier transform from Tukey and Cooley, and something that doesn't touch on my work, the integer relation detection algorithm, and then a fast multipole algorithm. So, pardon? Well, good choices, yeah. If you were going to invent them yourself, you probably would have agreed with many of those choices. Here's a piece you can just read on your own time about decision making and how you can try to use expected utility to decide whether it's reasonable to do things like buy. Whenever you buy something like a cell phone, they offer you insurance against things going wrong. And if you think about what's happening, you'll discover that most of those insurances are not worth buying. Basically, you're lining the pockets of the company rather than really helping yourself. So you can read about that in here. I think you might find that useful as well. I'm going to be talking about the Markup chain Monte Carlo idea today, and there's an excellent book on the topic if you want to go more deeply into things. It's called Markup Chain Monte Carlo in Practice, out of the Chapman and Hall series by Wally Jilks and Sylvia Richardson and David Spiegelhalter. Spiegelhalter being the guy and Jilks together, who were the principal co-developers of the WinBugs package that we're going to look at today. And I have abstracted from that book some chapters here on the course webpage, read in sideways on the PDF. So you'll find basic stuff about the nature of the Markup chain Monte Carlo algorithms, and then there's some other stuff in here you'll find useful as well. So that can give you an introduction to whether you like the book enough to consider buying it, for instance. Then I have a new problem set for you, and some partial solutions. I haven't finished the solutions fully, so I owe that to you in future. And then we'll have some backup information here in the form of handwritten notes, some of which I'll share with you today, and extra notes. And these things are always worth reading after the session is finished to help wrap up your understanding what's going on. And it says here in the extra notes, you can read chapter 2 of the draft book I was working on now, and that refers to a handout I gave you on the very first week, I think. No, it was on the second week. Chapters 1 and 2 of the Bayesian hierarchical modeling book. And if you go there on the web page and have a look at what's going on in the table of contents, chapter 1 is basically an introduction, and chapter 2 is it's going to cover some of the same ground that we're doing in here in about 80 pages of reading, so that'll be a nice backup for you on the MCMC stuff we're doing. And then let's see what else. And that pretty well gets us to everything that's here. Depending on how quickly we get through the MCMC stuff, we'll start the hierarchical modeling unit later today if we move quickly enough forward. The videos of last time's presentation will be up fairly soon, and there's some new R code down here and some new input files for doing the WinBugs modeling that we'll be looking at as we go along today. So that's the course webpage at the moment. And let's get back into part 3 of the lecture notes, which is on simulation-based Bayesian computation. And right at the end last time, I began to talk about the first page of this, but let's pick that up there again as a way to bridge with last time. Up until now, we understand the bones of the Bayesian paradigm quite well, I hope. One equation for inference, one equation for prediction, one equation for decision making. The inference equation involves bringing in information external to the present data set through the thing called the prior distribution. The bringing in information internal to the data set through the thing called the sampling distribution, which gets converted to the likelihood function by thinking of it as a function of the parameters for fixed data values. And Bayes' theorem says multiply those two and renormalize. There's your posterior distribution, which is your total information distribution. And we looked at some examples of how to make simple calculations in problems that have a relatively low degree of complexity. The heart attack case study with a binary a data stream coming toward you, and the Poisson case study involving length of stay for mothers who were giving birth to premature babies. And then we started talking about the NB10 case study in which someone very carefully weighed the same little block of metal 100 times, and we're trying to figure out what the true weight is. We fit Gaussian models to that last time and found that, learned how to fit them, but found that the model didn't fit very well. So today we're going to try to figure out how to do better. And so far, our only computational technique is what we called conjugate analysis, namely finding, if there were one, finding a conjugate prior for the parameter or the parameter vector, and then using the conjugacy to set things up so that the posterior had the same mathematical form as the prior. That way, if you learned how to manipulate that one particular probability distribution, then you have equal facility in thinking about it in the prior and the posterior. So and it had a number, conjugate analysis had a number of advantages. You recall we can express the prior information as equivalent to a data set, which we can often describe quite clearly. We can figure out how many observations there are in the effective prior data set, and the posterior mean then becomes a weighted average of the prior mean and the data mean. There were various other nice advantages, but so that's good. We get closed form results back on chapter 3 here of the lecture notes, but it's limited in scope, conjugate analysis, unfortunately, to a rather small set of models for which the results from conjugacy are possible. And that certainly stymied Mr. Bayes at the end of his life. He did not know how to make calculations in anything other than what we now call conjugate families. In fact, the only problem he ever tried was one that's just like our heart attack case study, where you've got a string of ones and zeros, and you have information external to those ones and zeros that you want to combine. Yes, please. Well, perhaps I shouldn't say that. He understood that the computation with the beta family, which we discovered was conjugate in the Bernoulli binomial likelihood, it came down to approximating areas under beta functions, incomplete beta integrals, and so on. And he was not the first person to encounter those integrals in calculus. Other people before him in the late 1600s and early 1700s had run into this function, and people already began to be able to get a bit of a numerical handle on it, even with paper and pencil in the middle 1700s. I don't know whether he tried any more complicated problems than that, but you can see in his writing that he himself can see that if you tried to apply these ideas to problems involving a vector parameter, he could see that it was going to get nasty pretty quickly as far as the integrations went. And then we had Laplace, who actually solved a number of important inference problems in astronomy and other fields by inventing Laplace approximations, which, as I said, I'll give you some insight into in a few weeks. But then that method was forgotten, and after Laplace died, people were back in the world of conjugate analysis, or else approximate analysis based on the hope that the sample size was large enough that the posterior would be approximately Gaussian, and so would the likelihood, and so then you could just use Gaussian calculations. So that's about where we were up to about the year 1940 or so, or maybe 41 or 42. And now we have these guys who are working on the Manhattan Project in New Mexico to try to build a bomb and win the war by building the bomb and dropping it. And they developed the need to approximate integrals that are just like Bayesian integrals, where you've got a parameter vector, and you're trying to approximate something that's a lot like what we would call a posterior distribution on a parameter vector. And they didn't have computers yet, but they knew that computers were coming because they were in good contact with Alan Turing, who was leading the effort at Bletchley Park in England to crack the German Enigma codes. And Turing informed them that he was already building the world's first analog computer to do the cracking of the Enigma codes, and he could see his way toward building digital computers. And he expected that by the mid to late 1940s, certainly by the late 1940s, there would be actually some commercially available machines, or at least machines that were at the level of usable in research at major universities, for example. So now here's this guy Metropolis, this applied mathematician Nick Metropolis, and he, and together with another excellent applied mathematician, or theoretical and applied mathematician, Stanislav Ulam, they realized that it was a game changer to imagine that you had a machine that could make very rapid calculations. That suggested to them a whole different way of trying to approximate integrals. And here's their insight, as we talked about at the end last time. The observation that they made, which had already been used implicitly by Mr. Gossett in his simulation study to understand how things work with the t-distribution, but the basic observation that Metropolis and Ulam made in the around 1942, and then they were forced to not publish until after the war was over by secrecy concerns for the government, is the following observation, that if you have a finite dimensional probability distribution, and the dimension can be practically as big as you want it to be as long as it's finite, anything you want to know about that distribution, you can learn to arbitrary accuracy by developing a way to draw samples, random samples from that distribution. And as long as you have A, a way to draw those random samples, and B, enough computing power to be able to draw many, many, many such samples, then we can see our way forward, as I'll show you today, to summarizing any aspects of a probability distribution, however high dimensional, as long as that dimension is finite. Terrifically cool idea, and in fact one that could not be put into practice for quite some time after they made that observation. That observation itself does not help you figure out how to actually approximate those integrals that Metropolis and the other people needed for the atom bomb project. That work was completed by other people, also with Nick Metropolis as the lead author, but not published until 1953. It's a paper that has 6 authors in it, including one author of which is the dreaded Edward Teller, the father of the hydrogen bomb. And so famous names on this Metropolis et al. Paper, in which they invented this thing that we now call the Metropolis algorithm. And once again, astonishingly forward-thinking for its time, because no one was actually able to use a Metropolis algorithm to actually approximate a Bayesian integral until the middle 1980s. And so they wrote something down and shared it with the world. And they got this idea around 1942. And so they were 40 years ahead of their time, largely because computers weren't fast enough yet to be able to use this. And also because, as I think I told you last time, there was a Tower of Babel with respect to the very existence of the idea. They published in the chemical physics literature, which statisticians didn't read, and they published their result in the language of chemical physics and trying to approximate integrals related to potential functions. No one in the statistics business among the Bayesians knew that the Metropolis paper existed and had solved the integration problem. along comes 1970, as I mentioned last time at the end, when a Canadian statistician named Hastings generalized the metropolis algorithm in a useful way. And he actually published that paper in Biometrica, which is one of the top statistics journals. But it was once again ignored by Bayesian statisticians because he again couched it in the language of statistical physics and potential functions. And so it didn't look like a paper on integration, to a Bayesian integration to the Bayesian, so they ignored it as well. Then these guys, these brothers, Gieman, Stewart, and I forget the brother's name, independently rediscovered a special case of the metropolis algorithm and published it under the name Gibbs sampling around the year 1981 or 82. But once again, they published in the IEEE Transactions, not in a journal that the mainstream statistics community read all the time. They explicitly wrote it out as, this is how we're going to approximate Bayesian integrals. So they were announcing to the world they had solved the Bayesian integration problem, but no one in the statistics community noticed because it was in the IEEE, one of the IEEE journals. And then finally, there was a meeting around 1988 when the Gieman showed up at a meeting with all these Bayesian statisticians, and the Bayesian statisticians were all moaning that they didn't know how to compute things. And Gieman said, well, we published something 6 years ago that shows you how to do it. Didn't you read the paper? And then finally the penny dropped, and that, coincidentally or not, was exactly the moment when desktop computers got fast enough that you could get a decent answer from MCMC work on a kind of overnight basis. An 8-hour run would get you something useful. So that's the background here, and that brings us up more or less to today. People in the statistics community have been taking the MCMC ideas that Metropolis and his colleagues developed in the 1940s and sharpening them in a number of ways since about 1990 or so. And we're going to look today at what the result is and use some software, some existing freeware to actually get the job done. So let's suppose, like it says here at the bottom, page 2 of part 3 of the organized notes, that suppose you're interested in a Pasteur distribution, P of theta given Y, where theta, I'm going to assume for now, is just a scalar, so a single number, and Y is, of course, a vector of length n, real numbers typically. And you're interested in a Pasteur distribution that for some reason cannot be worked with easily in closed form. And as I said initially, let's think about theta as just a number rather than a vector. Later on, we'll talk about the vector story. Well, you guys are all Bayesians now, so you know what you're interested in about Pasteur distributions. You'd like to know what the Pasteur mean is. I'll call it mu. It's just the conditional expectation of theta given y. You'd also like to know the Pasteur standard deviation, which I'll call sigma, which is the square root of the conditional variance of theta given y. You'd also like to know the shape of the Pasteur distribution. You'd like to be able to trace out its entire density shape by using something like a kernel density trace. And fourthly, if you are in the business of quoting intervals to people, which you should be, you want to be able to extract quantiles from this distribution, or inverse percentiles. In other words, to construct a 95% central Pasteur interval for theta, you would want to sketch the Pasteur and go 2.5% in terms of the area underneath the Pasteur distribution, 2.5% in the left tail, 2.5% in the right tail, and those two numbers represent the lower and upper limits on your 95% interval. So people call those the 2.5% and 97.5% quantiles, and sometimes people are interested in other percentiles or quantiles of the distribution, like the median, the 50th percentile also. So you can see basically we're interested in things like moments, first and second moments, means and standard deviations, things like percentiles and quantiles, and things like the basic shape. And now let's try to see how you would implement the Metropolis Ulam idea. Suppose you had some way to take an arbitrarily large random sample from that Pasteur, and let's call the resulting draws, random draws from that, theta 1 star down to theta m star, where m might well be a rather large number. Then if you think about it, it's not that hard to use those draws to actually come up with what we're going to call Monte Carlo-based estimates of all the things I just said you'd be interested in. For instance, if you had those draws, theta 1 star through theta m star, what would you do with them to come up with a good estimate of mu? Take their mean, right? And so all we need to know to come away from a data set like this with things that are interesting to us is standard Frequentis-style summary statistics for data sets of length, vectors of length m. So clearly, our estimate of the Pasteur mean which we could call theta bar star, would be just what you get by averaging the theta star draws. Similarly, if you wanted to know what the posterior standard deviation is, you just go ahead and take the sample standard deviation of the draws that you got out of the distribution. If you wanted to know what the distribution looked like, you could pass those numbers in R to the histogram function, and it would make a histogram approximation to the density. Or you could use the density function in R to get a kernel density trace, which is a smooth, kind of smooth version of something like a histogram with very narrow bars. So it's easy enough to estimate the density curve by standard things we do whenever we have a data set in front of us, a histogram or a kernel density estimate. And if you wanted to know where the 2.5% point is in the distribution, then all you have to do is to take the theta star values and sort them from smallest to largest and find where's the place in the sorted theta stars that has 2.5% of them to the left of it. That's your 2.5 percentile or your 2.5% quantile. And similarly for the other ones. And so here's the fancy way to write that idea. You solve this little equation for t, where we're, in effect, what we're doing is we're estimating what people call the empirical cumulative distribution function, f hat, for the uncertain thing theta, by simply counting up how many of the theta star values are less than or equal to t and dividing that by how many total draws there are in the data set. And so we force f hat sub theta of t equal to 0.025, and we know everything else in that equation except t, and now we can solve for t. So here, I of a is just the indicator function for when a is a true-false proposition. I of a returns a 1 if a is true and 0 otherwise. So that basically is one aspect of the Metropolis-Ulam idea. Take a very large sample from your distribution and then analyze it the way you would analyze any data set. If the draws really are correctly, identically distributed draws from that distribution, then things like sample means are good estimates of the actual posterior mean, and standard deviations and histograms or kernel density traces and percentiles and quantiles. I mean, it's right there in front of us. So pretty good idea, right? Now, one thing that's left open in this idea is how large should little m be, the number of replications, the number of random samples. How large should little m be in order to have a decent idea of what's going on? And by that I mean, think about that quantity theta bar star, which is, for instance, the sample mean of the theta star values, which is our simulation-based estimate of the posterior mean. Well, it's just a sample mean. And we can use frequentist ideas about the accuracy of sample means to figure out what its Monte Carlo standard error is. You see how we could do that? When we've got this data set, so let me make a little sketch here. When we've got this data set, so unknown to us, in terms of its exact structure, there's this posterior distribution. And so maybe it looks like this, I don't know. So this is the P of theta given y that we're trying to learn about. And suppose for some reason it's hard to work with it in an analytically tractable way. Then the idea is, if you can take a bunch of draws from this distribution, theta 1 star, dot, 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 down to theta m star, then we've got this thing that I'm going to call the Monte Carlo data set. That's going to be our name for this thing. And then later on, we're going to have something called the Markov chain Monte Carlo data set. So this one here is just the MC. MC has two iterations of MC. The first part stands for Markov chain, and the second part stands for Monte Carlo. Does anybody know why this stuff is called Monte Carlo? And who invented the name? You ever heard anything about this? It was actually Metropolis and Ulam who invented the name in that paper. And they were just basically noticing that what you're doing when you do when you do simulations from a distribution to learn about it, is that you are using randomness or chance in a controlled fashion to gain some advantage over the world, so to speak. And that's exactly what the casinos in places like Monte Carlo are doing. They're using controlled chance in a way to gain some advantage over the world, namely all those poor punters that are in there trying to win money and actually probably going to lose money. So they referred to it as Monte Carlo because they were thinking about what for them was the bastion of the world in which people were using controlled chance as a way to gain an advantage, namely think casinos like the ones in Monte Carlo. All right, so the mean of these numbers is just our old friend theta bar star. And the idea is that this is our Monte Carlo estimate of the posterior mean mu. And so over here somewhere on this on this curve here, we could find the balance point. That's the conditional expectation of theta given y. And because we are basing it on random draws from the distribution, of course, theta bar star is not exactly equal to mu, but it should approximately be equal to mu because we've used identically distributed draws. So that's my abbreviation for identically distributed as usual. I haven't yet said whether the rows in the data set are independent. The simplest way to do this is to have them be both independent and identically distributed, IID in other words. But one of the big insights of the Metropolis et al. Paper later on was that you actually don't have to have independence. And that's going to be an interesting thing for us to figure out today. So here's the deal. If you went and got M of these theta stars, you'd get a theta bar star. If I went and got a different M with a different random number seed, for example, from the same distribution, I'd get a different theta bar star from you, right? And so now what we're going to need is to come up with something that plays the role of a Monte Carlo standard error, which tells us something about how accurate theta bar star is as a Monte Carlo estimate of mu. And naturally enough, that's going to be driven by M in the obvious way. To get a really small Monte Carlo standard error, you're going to want to have M be what kind of number? Big or small or in between? You want little m to be big. And so this gives rise to an implementational question. How big is big enough? And that in turn depends upon what your actual accuracy needs are in the problem that you're working on. So let's go through that a bit. So I've already mentioned why they're called Monte Carlo estimates. And theory, based principally on what's called the weak law of large numbers, shows that with a large enough m, each of the Monte Carlo, otherwise known as simulation-based estimates that we just talked about, all four of them, including the, oh, I'm sorry, I'm on the wrong place. Thank you. So this is now page 4 of part 3. Theory shows that with a large enough value of little m, each of those four things I mentioned before, so the estimate, the Monte Carlo estimate of the posterior mean, the Monte Carlo estimate of the posterior standard deviation, the Monte Carlo estimate of the density curve, and the Monte Carlo estimate of the percentiles, all of those things can be made arbitrarily close to the real values in the actual posterior with arbitrarily high probability. But you have to make some reasonable assumptions about the nature of the random sampling. And of course, the simplest way, as I did mention a moment ago, is to make the sampling IID. And it's a fascinating fact that Metropolis et al. Exploited to tremendous advantage in their what we now call Metropolis algorithm paper, that IID sampling is sufficient but not necessary. In other words, if you can figure out a way to sample in an IID manner from a distribution, that's great and that will get you what you want. But actually, one part of the IID story is not really necessary to still make the thing work. So IID has two parts to it. The first I for independence and the second ID for identically distributed. We cannot give up the ID part, right? Because you have to be validly sampling in an identical distribution fashion from the actual distribution you're interested in. But it's going to be interesting. It'll turn out that we can give up the I, the first thing. You don't have to make the draws independently as long as they're all identically distributed from that distribution. We can use basic facts about what are called stationary time series to figure out what's going on. Well, the simplest, most straightforward way, you don't need independence, first of all, and I'm going to show you that later today. In the simplest way of processing the data, you do need identical distribution. If instead you had some way of drawing from a distribution that's not quite the right one, you might be able to find some clever way to adjust the draws to make it the right answer for the one that you care about. And there are algorithms for things like that. But absolutely the most straightforward thing would be to find a way to sample in an IID manner from the distribution and go from there. So for example, if theta bar star is based on an IID sample of size little m from the posterior, we know from our earlier discussion of frequentist inference that in repeated sampling, the variance of what is now the random variable theta bar star, and the random variable part comes from our own Monte Carlo work in drawing from the posterior, that variance is just sigma squared over m, our old friend. So the square root of that would be sigma over the square root of m, our old friend for the formula for the standard error of a mean. Here, sigma squared, as before, is the variance of the posterior. And evidently, to construct a Monte Carlo standard error, I just estimate sigma by sigma hat, namely the sample standard deviation of the theta star values, and divide by square root of m. And that's going to have something I'm going to call the estimated Monte Carlo standard error of the Monte Carlo estimate theta bar star. And I notate that, or I denote it by putting a hat over the SE, which means estimated standard error. The true standard error is sigma over the square root of m, but that formula is unusable because I don't know what sigma is. So I'll use the working formula SE hat, which is sigma hat over square root of m. And we can get our sigma hat directly from our data set, our Monte Carlo data set. And so now we can experiment a bit, possibly after making a preliminary run to get a preliminary estimate of sigma. We can experiment around to decide on m based upon what our accuracy need is. And so let me give you an example. And later on, I'm going to call little m the length of the monitoring run, which is why I chose little m as the name for it. It goes along with the word monitoring. So here's an IID example. Let me consider the posterior distribution in that length of stay example we had before. So you remember the sampling distribution in that example was Poisson, and the conjugate prior for the Poisson parameter is the gamma. And so we found that the gamma, the posterior distribution for lambda given y in that example was a member of the gamma family, and it turned out to be the one with the prior we used with alpha, the first parameter of the gamma family, having value 29.001, and the beta having the value 14.001. So we already know from basic properties of the gamma distribution that the posterior mean of lambda in this example is just the alpha over the beta, which comes out around 2.071. And I bring this up because when you're trying something new, one of the best ways to see whether it's any good or not is to fire it up on something where you already know what the right answer is and see if it gives you back the right answer, right? So here's a little example where we already know what the right answer is. Let's see what happens. So I've written a little R function and posted it on the web page for constructing Monte Carlo estimates of the posterior mean and Monte Carlo standard error values for those estimates. So it's a function called gamma.sim, and let me describe to you how it works. When you write functions in R, the first line says gamma.sim is assigned the value of the following function, and you construct the assignment operator in R with the composite symbol less than or equal to sign followed by a dash, which looks like an arrow pointing to the left. Or you could equivalently use the symbol equals, and that would also serve the assignment purpose. I don't like that notation so much because equals gets used for other reasons in coding of this kind. For example, asking if something is equal to something else. So I prefer to use the little arrow notation, which you construct by using 2 keystrokes, but rather than 1. But there you go. And then the way you construct a function is you say function as your generic name for it, open parenthesis, and you list all the arguments to the function, the inputs to the function. And then you start a left curly brace, and you write some stuff for a while until you get down to where there's the final right curly brace that closes the left one, and that finishes the function. The function does not all have to be all on one line. R understands that once the left curly brace is open, it's collecting the commands in the function until you give it the final right curly brace. Okay. Here I'm going to give it as inputs little m, the number of observations going into each of the theta bar stars. And I'm going to give it the alpha and the beta I want to simulate from in the particular gamma distribution. Then I'm going to ask it to do something over and over again a bunch of times, and that number of replicates I'm going to call n.sim. And the last input to the function is a random number seed. Of course, as you all know, computers don't actually generate truly random numbers. They generate these things called pseudo-random numbers using algorithms that are largely based on number theory. And you need to initialize such an algorithm with a seed which typically takes the form of a large positive integer. And that way, once you've passed the seed argument into the function that you're writing, anyone else can run that function afterwards with the same seed that you gave it with the same seed that you used and get exactly the same results from R. Otherwise, if you don't use that, then 2 people running the same function will get slightly different answers because of Monte Carlo noise, and then people might think there's something wrong with the function. So it's always good to, whenever you're about to do something of a Monte Carlo nature, pass into your function the random number seed and take care to initialize it the way you want and share that with someone else who's going to try to replicate your findings. So there's a built-in function in R called set.seed, and you simply say set.seed left parenthesis, and then you mention the large positive integer of interest to you and close parenthesis. That makes your function replicable. Then I'm going to create an object called theta.out that gets returned outside the function. And I can do that by making it a matrix filled with zeros. So the first argument in the matrix function is what you want to fill the matrix with. And then the next argument is how many rows you want it to have, in this case n.sim, and how many columns is the next argument do you want it to have, namely 2. And then I do a loop, which is done in R with the for loop construction, similar to in Fortran, except here I say for left parenthesis I in 1 colon n.sim, close parenthesis, and then I start another left curly brace. And so that says as the looping integer, the looping index little I runs across from the integers running from 1 up to n.sim, do the following stuff, please, R. And the following stuff is the stuff that's in the next set of curly braces. And so I've opened a curly brace on the for line, and I close it 3 lines later with another right curly brace. And what I'm going to do over and over again is I'm going to take random samples from the gamma distribution. So I say theta.sample is assigned the value of R gamma. That's the function in R. The R part means random. Take random draws from the gamma distribution. So I use the R gamma function. And the first argument, M, is, well, how many samples do you want? And so I say, M of them, please. And then which gamma distribution are you thinking of? And I say, well, it's the one with shape alpha and scale equal to 1 over beta. You may recall from one of our earlier meetings that R does not use the same convention about the role of the scale parameter as I find most natural. Sometimes people write the function in the form beta to the alpha e to the minus beta times the argument, and sometimes they write it like that, except the thing that acts like beta is more like 1 over beta. And so here, to get the function to do the right thing, I had to tell it that the scale parameter was equal to 1 over what I'm used to calling the beta parameter in the gamma distribution. And having defined this thing called theta.sample, in the ith row of the theta.out object in the first column, I store the mean of those theta.sample numbers. And in the second column, I store the Monte Carlo standard error, the square root of the estimated variance of those guys divided by how many there are. And then after I get out of the for loop, I just return that theta.out object, and that completes the function. So like it says below it, this function simulates n.sim times the process of taking an IID sample of size little m from the gamma distribution with parameters alpha and beta, and calculating the Monte Carlo estimate of the mean of that distribution, theta bar star, and its Monte Carlo standard error. So now let's go into R and actually do it. So I'll go back to the course web page and click on the code called IID simulation from a gamma posterior distribution. So I've given you all the code that you need to actually do this if you want to try it yourself as well. So I'm going to grab the gamma.sim function, and I'm going to set some values of interest to me. I'll set m to be 1,000 just to get a sense of how accurately we can learn about the posterior mean with 1,000 samples in the Monte Carlo data set. The alpha and the beta, we already agreed, had those values that they were in the case study. And I'm going to do this 500 times just to see how different the answers come out each time. And I'll give it some big positive integer seed like 9626954. And then I'll run the function theta.out with those particular values and ask it to tell me what the first 10 rows of the matrix are. So I'll fire up a copy of R now, and just paste all that stuff in and let it run. And it says, well, okay, there weren't any errors. When you write your own first R function, that won't be true. That will manifestly not be true. In fact, the first time I ran this function at 3 o'clock this morning to get ready to meet with you guys today, the function gave rubbish. And it was because in between the time I had originally written the code and when I'm using this version of R, they changed their convention on how to work with the scale parameter. And so I had 1 over the right scale parameter. So I had to go back and figure out what was wrong and change the scale parameter. And then, of course, now finally the code does work. And what we see is 10 replications of the process of taking a sample of size 1,000 from this beta distribution and calculating the mean of those simulated draws and the Monte Carlo standard error of that mean. And so we know from what we said back here in the notes that the right answer is 2.071. That's the right answer from theory. And so each of the numbers in that column that has values like 2.05, blah, blah, and so on, each of those should have been around 2.071 if the simulation's working okay. Do they all seem to be kind of around 2.071? Yes. The other numbers in the final column of this little table are the Monte Carlo standard errors that get attached to each of those Monte Carlo estimates. And what they're saying is that every time I do it with 1,000 numbers going into this simulated data set, I have learned the posterior mean up to a Monte Carlo plus or minus of about 0.01. And that standard error has the usual meaning. If I really wanted to know what the posterior mean was, I could take that number and multiply that 0.012 by roughly 1.96, and go 2 of those either way. And that would be my Monte Carlo confidence interval for what the real posterior mean is. And you can see that means it's probably somewhere around between about 2.05 and 2.09, based upon the accuracy that we have right here. So that seems to be working so far. Let's take it a little bit farther. And so here in the code, I've reproduced those same things. The comment function in R is a sharp sign or a hashtag. And so I put into the code here what you expect to see but in comments. And so if I had run that code along with R, the other commands, and put it in here, what we would have seen is that in blue was what I actually got when I ran the function, and in red is what I should have gotten if everything went well, and you can see they do match perfectly. All right, so let's go back to the narrative here on page 5 of the handout. So here I have a little session in which I'm using R in my Unix machine back at UC Santa Cruz rather than here in the Windows world, but of course you get the same thing either way. And you saw this stuff is fast. It's very fast indeed. And what we see here is that the theta bar star values fluctuate around the truth, 2.071, with a give or take of about 0.012. And that actually agrees well with the theoretical standard error, because we know that the variance of a gamma distribution is alpha over beta squared, and therefore the standard deviation would be the square root of alpha over beta, and so sigma over the square root of m would just be the square root of alpha over beta times m, and that comes out 0.01216. And so not only are all those Monte Carlo estimates of the true posterior mean approximately right, around 2.07, but look, all the Monte Carlo standard errors are about right also. They're all supposed to be about 0.01216 in size, and you can see that the 0.012 part's pretty solid, and then you get a little fluctuation out in the third significant figure. So basically what we've learned is that we have been able, with 1,000 draws, we've been able to pin down the posterior mean 2.05 roughly, down with a Monte Carlo standard error of about 0.01. If you wanted 3 decimal places after the 3 figures after the decimal place, is 1,000 for a Monte Carlo sample size enough? If I wanted to be able to say that I think it's 2.050 and have all 4 of those significant figures pinned down, is little m equals 1,000 enough? No, in fact, it's rather sharply not enough, because all we've got now is an accuracy down to about 2 figures after the decimal point, and we're going to need to work a bit harder to get that third one. There's a function in R called postscript, in which I think I may have mentioned this before. I forget, but I'll say it again. You start the postscript function by naming a file that you want all the remaining plotting commands to be spooled into. Double quote gamma.sim1.ps, gamma-sim1.ps is the file I used in this case. And then I run some commands that create a plot, and when I'm done spooling to that postscript file, I issue the command dev.auth open close parenthesis. And so that's a way to create postscript files that you can insert into documents, like I used to create this PDF of the lecture notes. And they also have a command called PDF instead of PostScript if you want to go right to PDF. So what's going on here? Let me explain what I did. Well, we know that each of the theta bar star values is the mean of 1,000 IID draws. And we know that the central limit theorem says that as long as the number of values going into each mean, which here is called little m, is big, you're going to get a nice normal curve for the repeated sampling distribution of those theta bar stars. And so I can make a normal quantile plot to see whether they are rather normal. That command in R is called QQnorm. And so I'll pick out the first column of the theta.out matrix, which has n.sim rows in it. And I think I used n.sim equals 500. So there's 500 replicates of this theta bar star guy here. And I will I'll assign that particular column of the theta.out matrix to this new vector called theta.bar. And I will standardize that by subtracting off its mean and dividing by its standard deviation, or equivalently the square root of its variance. And I'll hand those numbers to QQnorm and then plot the line that it's supposed to follow, namely the line y equals x, which you generate in R with the command abline, an absolute line just being described in absolute terms in terms of its slope and intercept. And you mentioned the intercept first and then the slope. So let's do that in R. I'll go back and grab that code. Here I don't really want to create a PostScript file, so I've gone ahead and commented that out. And when you're done with the dev.off, it tells you, often tells you what is the current plotting window. And so here it says null device, and that means it's just returned you to the window that you were in before. So I'm going to run this stuff now and see what we get. And so, and the answer is, these things were supposed to look like draws from a normal distribution, and by God, they are. Even though the distribution we're sampling from is a skewed distribution with a long right-hand tail, 1,000 draws going into each one of these theta bar stars is plenty, way enough to get you a nice normal curve here. And so when you plot the sample quantiles on the vertical scale against the numbers that you should have seen, that's how a normal QQ plot works. The vertical scale is the actual numbers in your data set sorted from smallest to largest, and the horizontal scale is what those numbers should have been if the distribution follows the normal curve well. And of course, if they do, if the distribution does that, then you should get something quite a lot like a straight line. And here it should be the identity line because I standardized those theta bar stars. And wow, this is a very nice normal QQ plot showing just what I expect. Okay, and so there it is here inside the PDF. And I can also build a little for any one of these. Well, no, here's something I can do even more stringently. I can, sorry about that, I can, since I have 1,000 of these guys, and each one has an estimate and a Monte Carlo standard error connected with it, I can start at each of those estimates and go roughly 2 standard errors either way and build that 95% confidence interval I mentioned to you. And then I can empirically compare all those 500 intervals with the actual number, correct answer, 2.071, and see how many of those intervals include the truth. And if everything's going fine, since they were nominal 95% intervals, about 95% of them should include the truth. So let's try. So I'll go back and again grab the code and have a go. So I generate something called truth, which is alpha divided by beta. Then I grab the standard errors out of that second column of the theta.out matrix and put them in the place called theta bar star. I remind myself that the 0.025 quantile of the standard normal is about minus 1.96. And so then I do something a little complicated. I say, well, please, R, would you construct the vector of the form theta.bar minus 1.96 theta bar dot se. It's going to go in to each of those rows of the theta.out matrix and pick out the theta bar star that is in there and the standard error that goes along with it and go 1.96 of those standard errors down below and see whether that's smaller than the number truth. And so this whole thing here is going to be a logical statement. R is going to say, oh, you asked me to see if something's true or not. So that whole thing is going to come out with either a true or a false. And then at the same time, I wanted to see whether the upper limit of the interval is larger than truth. And so that's going to be another true-false statement. And then when you multiply 2 true-false statements together, R says to itself, now wait a minute, you can't multiply true-false statements together. But oh, I know what he means. Let me convert true into 1 and false into 0 and multiply the 1s and the 0s. And so that works fine. So then all of this stuff inside the sum command will turn out to be 1s or 0s. And I simply sum all the 1s and 0s and divide by how many there are. And that gives me a sense of how often my intervals actually include the truth. And that's supposed to be around 95%. And R says, oh, I forgot to bring the row called truth into there. So let's grab that also. It's funny. I thought I did bring it in. Let's Control-C that guy. And Control-V this. And it says your allegedly 95% intervals covered the truth 95.4% of the time. So I'm pretty happy. This is all going just the way it should. Okay. And so basically the idea here is that right in the middle of a Bayesian calculation, we can use frequentist ideas to work out how big the Monte Carlo sample size, little m, needs to be to have any desired Monte Carlo accuracy for things like the theta bar star as an estimate of the posterior mean and so on for the other quantities. This is one reason why on the very first day I suggested to you that in the 21st century, anybody who wants to know how to think intelligently about uncertainty would be well advised to learn quite a bit both about the Bayesian paradigm and the frequentist paradigm. And we see an example of that right here. Right in the middle of a Bayesian calculation, we find it very useful to know how to reason like frequentists in order to see what's going on inside the Monte Carlo data set. So we're using frequentist ideas to create Monte Carlo data sets. Later on, we'll be using frequentist ideas to create Markov chain Monte Carlo data sets. And then we'll use frequentist ideas to analyze them as a way of getting approximate Bayesian answers. So a nice unity between the two ways to think about probability. Well, in practice with the entire posterior distribution unknown, the way you would basically arrive at how large little m should be is something that you may have seen before whenever you were answering a sample size question of your own in your applied work. If you don't know much about what's going on, it's helpful to take a little preliminary sample and get some estimates of things like uncertainties in the preliminary sample and then use them to estimate how much data you really should have. And that second number will usually be larger than the sample size in the preliminary sample, so then you go back and get more data until you have the accuracy that you want. So you would probably take an initial sample. Here I might choose 1,000 like I did in this example here, and then look at the Monte Carlo standard error to decide how big the little m actually needs to be. And so here I can imagine running the function gamma.sim with an m of 1,000 to get one particular replication of the Monte Carlo data set, and I'll put a 1 right there to say I only want to do this once, please. Would you please do that for me, Mr. R? So I'm going to go back here and do that. So I'll print this once. And this is a thing you can do in R where you can stack commands. So I create a command called please assign to the place theta bar the value of what you get by running my function gamma.sim with that stuff there. And then I can embed that in another function. So I pass the result of that particular function to the print function. And so what as a result happens is that it both does the stuff inside the print parentheses and then writes out the answer. So that's a slick way to get two things done with one command. And so here I've done the thing once, and it's just an example of what you saw before. It's got a 2.05 roughly for its estimate of the real posterior mean and a standard error of about 0.012. And now, having gotten that particular standard error, I can work backwards to see what the sigma was, and then that'll give me an estimate of how many observations in the Monte Carlo data set I really needed. So look at equation 3 here on this page. Suppose I wanted the Monte Carlo standard error to be some small number like epsilon 0.001. Then you would just set the standard error equal to epsilon, so sigma hat over square root of m is epsilon, and solve for m. And you get an unhappy formula. What it says is that the smaller epsilon is, the bigger you need, Monte Carlo sample size you need to be able to get the accuracy you want. And what's worse, that idea of the tolerance goes in as the square of the small number in the denominator. So this is part of the square root law for how uncertainty goes down. And also, your uncertainty is driven also by the posterior standard deviation. The noisier the distribution is we're sampling from, obviously the more draws we need to be able to learn about its mean. And that, unfortunately, appears in the numerator also as a square. And so everywhere you look at it, this formula right here, formula 3, is bad news, but it's actually the news. There isn't any easy way to make it any better. So now having worked out the value to 0.0121743 for the Monte Carlo standard error. That means that sigma hat over the square root of 1,000, which was my original m value, is that value there. I can solve that backwards and work out what sigma hat is. And now I can stick the sigma hat into the numerator of this formula here to get an m hat and put in the 0.001, and I get a forbidding looking number. To get epsilon of about 0.001, I would need to draw almost 150,000 draws from this distribution. Now, if this really were back in 1989 or 1990, that wouldn't sound like much fun, but our machines are so fast now that 150,000 draws from a univariate distribution is over in much less than 1 second. And so we live in a moment when computers have finally gotten fast enough that we can overcome whatever inherent noisiness is present in the Monte Carlo method simply by taking an enormous number of draws and swamping out the uncertainty by taking a large number of draws. And the computers are fast enough now to make that a realistic strategy. I see that we're already up to our first break, so